Section 4.3 discusses the complementation rule and conditional probabilities. I'm not going to go into conditional probabilities here so much, but we are going to use the complementation rule. You're going to see it later on in the course, and that's certainly one of the things that I'd like you to get out of this section. We're actually going to start with one of your homework problems, Abby, and that'd be problem number 5. Problem number 5 asks you some questions about a couple that has 3 children. So find the probability that when a couple has 3 children, at least one of them is a girl. For your convenience, on your handout, I've given you the sample space of what can happen when you have 3 kids, the genders of those 3 kids. So that would be these right here. So those are all the different things that can happen. And we're interested in trying to find the probability that at least 3 of them are girls. Now, we're going to make an assumption here that the chance of a girl and a boy are equally likely. In fact, they're not. 51% of the time, people have boys, and then the rest, people have girls. And it changes depending on your country. China's being an extreme example there. But we're going to assume that it's a 50-50 chance, making these points equally likely. What I want you to do is circle the events that represent having at least one girl. So in your sample space, go through and circle the events that represent at least one girl. You should be circling a lot. Basically, you should be circling almost everything, right? What's the one thing that you didn't circle? All boys. So kind of going back to what we looked at in section 4.2, there's a couple different ways we can calculate the probability of at least one girl. You could calculate it directly as the probability of all 3 girls, or this one, or this one, or this one, all 7 of these things. But that feels like the long way. Can anyone think of a shortcut to calculating this probability? Well, I'm talking about not the answer, but a shortcut to how we calculate it. Connor. Yeah. So we're going to do it as 1 minus the probability of the complement. So 1 minus the probability of all boys. Oh, boys. So another way to look at this is kind of on this line here, and that is probability of at least one girl. That's all of these things. You could have 1 girl, 2 girls, or 3 girls. Or the complement to that is right here. No girls, or all boys. And it's going to be easier for us to calculate one as opposed to the other one. At least one girl. No girls, or all boys. The nice thing here is that there's just that one probability to calculate. So probability of all boys is probably a boy on the first one, and a boy on the second one, and a boy on the third one. Now here's where something from the last section comes into play too. These probabilities, are they independent or dependent? That is, if you have a boy the first time, does that increase or decrease or affect your chances of having a boy the second time? No. Still a 50-50 chance. They're independent. So this is 1 minus the probability of a boy on the first one, and the second one, and the third one. And as we said earlier on, we're making the assumption that these probabilities are exactly 1/2. So 1 minus 1/2 cubed, really 1 minus 1 over 8, is 7/8, which is what you said a while ago, but I just needed to go through all the calculation here, because we're going to do the complementation rule a couple more times here. So there's a couple nice things that we did in calculating this probability. We used the complementation rule. That's what really got us started. And then we also used the independence of these events, and that kept us going. How are we looking with question 5 here? We're okay on that one? A and A? All right. Let's try another one similar to that one. Problem number 8. In China, where many couples were allowed to have only one child, the probability of a baby being a boy was 0.545. So that's really high. And I'm not going to discuss why that might be high, but maybe you know. In any case, among 6 randomly selected births in China, what is the probability that at least one of them is a girl? All right, could this system continue to work indefinitely? Well, it's the author again, expressing a little conscious, which is fine. We want to find the probability of at least one girl in the 6 births. So let's see what we can do about that. What numbers should I circle? What satisfies at least one girl? Julian, maybe you can help me out. What numbers should I highlight or circle here? Some help, maybe? Let's see. I picked let's see. Jason. No, not Jason. Ryan. All of them except what? Yeah, all of them except 0. So that's a probability of at least one girl. Now, calculating this directly would mean the probability of finding one girl plus the probability of finding 2 girls, 3 and 4 and 5 and 6. It'd be a real pain. You really wouldn't want to do it this way. Not without some help. But help is at hand, right? Because we can calculate this with the complement. The probability of at least one. How are we going to calculate it? 1 minus the probability, yeah, of all boys. All boys. Or 1 minus the probability of no girls, of none. So 1 minus probability of all boys is 1 minus probability of a boy on the first one and a boy on the second one, all the way down to the last one. There's an important assumption that you need to make, but that we can make here. What's that important assumption? They're independent. You know, what happens with one couple's child is not going to be dependent on what happens with another couple's child. So by independence, I can multiply these probabilities together. Probability of boy 1 times probability of boy 2, all the way down to 6. Let me let you look back at the problem here for a second, because I need you to tell me the probability of a boy for this problem. Perfect. 0.545. So 0.545 0.545. Okay, so 0.545. And there's 6 of them, right? So 1 minus 0.545 to the 6th power. And that should be pretty high. It should be a good chance that amongst 6 girls, or 6 births, that you get at least 1 girl. So 1 minus 0.545 raised to the 6th power, 97.38% chance. So about 0.9738. Okay. So another nice example of the complementation rule. How are we looking on that one? Are you ready to try one? All right. I'm going to have you try problem number 10. It's going to be very similar. You're just going to have to think a little bit for yourself what to do to get this probability down here at the end. Because it's going to talk about test taking, the SAT, and guessing. So, let me zoom in a little bit. If you make random guesses for 10 multiple SAT test questions, each with 5 possible answers. Now I'm assuming that even though it has 5 possible answers, how many are right? 1. Just 1. So 1 out of the 5 is right. What is the probability of getting at least 1 correct? So if these questions are part of a practice test and the instructor says that you must get at least 1 correct answer before continuing, is there a good chance you will continue? So your goal is to find the probability of getting at least 1 correct. You're making 10 guesses. What's the probability that you get at least 1 correct? Now, if you'd like, I've got this here on your handout, like we've done for the last 2 problems. Try and push you, guide you into using the complementation rule. That's how you're going to calculate this one. Believe me, you wouldn't want to do it any other way. There's the problem. Help each other out. This is a big enough class that I can't get around to everybody. So help each other out. And I'll try and walk around and help out as well. numbers should just get the probability. You can borrow them. I have some that I bring you can borrow. Well, how are we getting wrong? If there's 5 choices, 4 of them are wrong, it's a probability of getting one wrong. Well, how many wrong guesses are there? Each problem has A through E, right? A, B, C, D. Only one of them is correct. So at least 4 of them are wrong, right? So your chance of guessing wrong are what? Out of 4 or 5. Yeah, 0.8. So there's a 0.8%, or 0.8 would be that probability. Probability of the wrong one there. And then 0.8. All of these. Okay, good. So what you need to understand here then is the chance of guessing wrong. So there's 5 possibilities. How many of them represent wrong guesses? 4. So your chance of guessing wrong are 4 to 5. Yeah, 4 to 5. Okay. If it locked my screen, I'm so annoyed. Extra credit for somebody who gets me a Macintosh.
Can't you change the timeout on it in the settings?
Maybe. You got these things locked down pretty tight. I can't do anything on it. It's annoying. Okay, so probability of at least one correct answer. So probability of at least one correct answer really reflects any of these events. At least one correct. And rather than calculate all these different probabilities and add that up, we're going to take the simple expedient of calculating the probability of getting one wrong, or none of them right, and then subtracting. So probability of at least one correct is going to be 1 minus the probability that they're all wrong, which is 1 minus the probability that the first one's wrong and the second one's wrong, and so on, all the way down to the last one. Now, if you're just guessing, then these probabilities are independent because it's just random. So it's going to be probability of the first one wrong times the probability of the second one wrong. What's the probability of getting one of these things wrong? Well, there's 5 possible answers. 4 of them are wrong. So it's 1 minus 4/5. And somebody wrote 0.8, and that's fine. 1 minus 4/5 to the 10th power. I think out of convenience on my calculator, I'm going to use 0.8. Should get about 82 or 89.26% as your final answer. So just a little bit under a 90% chance of getting at least one right. You have to be a little bit on the unlucky side to not get one right, but it could happen very easily. Okay. How are we doing on the complementation rule here? Okay. All right. Let's do one last one here. It's problem number 14. It's a little bit different. We've got this table of students who were given same amount of money, and people watch what they did with it. So chances are, and I haven't looked through the book entirely, we'll probably see this table again in future sections. Seems to me it would be a good table for other types of problems. So students were given either 4 quarters or $1, and they watched what they did with the money. Problem A says, find the probability of a randomly selected student who spent the money given that the money was a dollar bill. So let's see if we can't write that. Probability that they spent it given that they were given a dollar bill. Well, let's see here. Amongst the people who were given the dollar bill, how many spent it? This part right here says, okay, we're just going to focus a little bit on this part of the table. We're not looking at the whole thing anymore. Not looking at all 89 kids in this experiment. We're just looking at those given a dollar bill. So what's the probability that they spent it amongst those people who were given a dollar bill? Go ahead. Yeah, 12 over 46. Let's take a look at the probability that they spent it given that they were given 4 quarters. Given 4 quarters. So now we're looking at a different part of the table, right? You're looking at this part of the table. What's the probability that they spent it? Somebody else. Yeah, thank you. 27 out of 43. So this first one is about 0.2609 or 26, about 26%. The second one, well, that's more than 50%. So it's 0.6279. So does the type of currency they were given affect the probability of them spending it? Absolutely. Are these two variables independent? Whether or not they spend something and what type of bill or what type of currency they're given, are those independent? Let me ask it a different way. Does the type of bill or the type of currency you're given affect your probability of spending your money? Yes. So they're not independent, are they? Because the outcome of one affects the probability of the other one. So they're not independent. These are dependent events. Dependent events. Cool. For homework in this section, try problems 1 through 11.